Let's review what we went through in the last lecture. So one single important thing is the chart we have. That's what we have, the Kc number, Kc over pi equals h over d, and this is the diffraction number, delta over pi d over lambda. So you're going to pay attention to this because it's important in terms of everything. Okay, how do you make a decision based on this chart? Which method to use to compute the wave load? So we have Kc number and diffraction number. In general, if we want to use Morrison equation, we have to have a very small diffraction number, which is 0.04. That's d over lambda less than 0.04. In this region, we can use Morrison equation. Okay. We also have to check the Kc number. This is 1. If the Kc number is smaller than 1, we have to use diffractional theory in all this area. Right? And this is for Morrison equation. So in this small box, we can use both Morrison equation and diffraction theory. In addition, we can also use the Froude-Krylov method. So 3 methods apply in this region. This is essentially the results of a dimensional analysis. And after I introduced you this chart, we went through the Morrison equation and how to determine the inertia coefficient, the drag coefficient, and I talked about the Froude-Krylov method. And that's you in this region you assume the diffraction from the structures is small, and you find the pressure around the structure surface, and then do integration to find the total force. And I also made a very brief introduction to the diffraction theory, where you have incident waves, you have diffracted waves. How do you write the governing equations? How do you find out the boundary equations, boundary conditions? Okay. This lecture, I will make a brief introduction on the current and wind load. This is not good. Introduction to current and wind load. Current and wind loads on ocean systems have many similarities, despite the fact that the water and air have very different mass density, rho, and the typical velocity in magnitude. The density for water, here we're talking about seawater, right? About 1,000. And air close to 1. And for velocity, typically we're talking about the for sea current, we're talking about on the order of 1 meter per second. For water or current, we see seawater. For wind, we're talking about on the order of 10 meter per second. Okay, so there are many factors to characterize the flow, and there are very many important effects to consider in the characterization. One of the most important parameter is the Reynolds number. Bless you. Which is defined as here. Here we assume U is the characteristic velocity, D is the length scale, structure length scale, nu is the kinematic viscosity. For wind and current load problems, we're typically talking about high Reynolds numbers. High Reynolds numbers. So on the order of 10 to the 7th. Another parameter is called roughness number. It's defined as K over D. Here K is a roughness length scale of the structure surface. K is roughness length of the structure surface. Other important effects to consider is the geometry of the body. Geometry of the body, and okay, and also nature of the flow. What I meant by nature of the flow is like the flow is more steady, or there's much fluctuation in the velocity or the direction of the flow, and there are many other effects. Okay. In general, the current and wind loads are difficult to predict theoretically with sufficient accuracy. Because theoretically with sufficient accuracy. Can you see it if I write it this slow from there? No? Okay. So because first, most of the time we are dealing three-dimensional problems. And And the second of all is the nature of the flow. It's quite often is turbulent flow. There are lots of fluctuations, also the flow separation due to the presence of the structure, and also the weak interaction. So typically we have to use empirical formulation to predict the current and wind loads. So, and quite often we have to assume a steady state, steady flow. We use the mean velocity, etc. Okay. What happened? Okay, now let's talk about current first. From a design point of view, ocean current velocity can be divided into several components. The total current velocity is this many components. The first term is tidal component. And this one is wind-driven current due to wind-driven current. And this is Stokes drift. And this is due to ocean circulation. And this is due to storm surge. And here is the local density, due to local density variation, like the cause for the internal waves, the present internal waves, and ocean circulation, all due to the shape of the continent, like a loop current in the Gulf of Mexico. Okay, I just show you two examples. For the tidal component, we typically write it this way. This is from h minus 10. This is so typically, if you draw a picture of this this profile, you'll see it's like this is the mean water level. This is the h is the depth of the water depth. You'll see a constant current here, and the end you'll see decay to 0. Okay. For the wind-driven current, so UW is quite often written as UW as 0. This is for so H0 is typically 50 meters. If you draw a picture of this, it's like water minus H0. This is 0, right? This is the wind-driven current. Okay, in general, current can penetrate great water depths. So field measurement showed that in water depth of up to minus 900 meters, we still have strong current. Strong current, I mean the current velocity is, approximately 0.5 meters per second. That gives us an issue when we design the risers and mooring lines. We have to consider the VIV or the current force, a lot of things. And on the surface, the current velocity can be up to around 2 meters per second. This is a very strong case. Okay. This is a rough introduction to the current. About wind. So in design, wind speed is typically computed based on average okay.
What's the minimum of H0?
H0 is just water depth, arbitrary water depth. Typically, we see for when we compute the wind-driven current, we set H0 equal to 50, which means the wind can affect the current up to water depth to minus 50 meters. So here, this is current due to wind blowing, right? Yeah. So wind blowing introduces a shear stress on the surface. The shear stress can drive the water go this way, right? Yeah. You can imagine at the surface that the velocity is larger. As the depth goes larger, the velocity of the motion is smaller. So it means the water at this part is less affected by the wind. So after certain depths, you typically don't see any motion of the water. So if we, talking about wind-driven current only. Oh, okay. If when there are empirical measurements, those are based on observations. This is typically equals to 0.02 U10. Here U10 means the wind velocity at 10 meters above the sea level. So like if I have 50 meter per second wind at 10 meters above the sea level, we can estimate the current at the surface. It's about 1 meter, right? 1 meter per second. Well, this is different. This is not universal. From measurements, at different locations, different size of the globe in the ocean is probably different. It's a lot of there are a lot of effects to consider. But just give you one example. Okay. So in design, wind speed is typically determined as the average over a prescribed period. So for example, in the North Sea measurement, we can have extreme wind speed, wind velocity go as to 40 meters per second. This is a strong wind. Okay, so in design, another factor we have to consider is the fluctuating wind force due to gust. It's like all of a sudden there's a strong wind coming, and for a very short period. This can excite give the structure an excitement, may cause the resonant response. So we have to consider the fluctuating force. Of course, it's wind force due to gust. So as I mentioned here, the wind speed, we specifically see wind speed at 10 meters per height because the wind profile over the sea, suppose this sea, this is a vertical plane Z, the wind profile can be a function of the height above the Suppose this is 10 meter, then the wind speed you measured is U10. This is a very common term in oceanography. Okay, we have to know the wind profile as a function of height above the sea level in actual design. So the last fact is wind and waves quite often present at the same time, because most of the times, surface gravity waves is generated by the wind. So quite often we need to know the joint probability between the wind and wave. So it's like for 10 meter per second wind blow for 2 hours, and then what is the most possible significant wave height, the wave spectra, things like that. Okay. This is a general introduction to the current and wind. Now let's start with a very simple example. That's a steady incident flow past a circular cylinder. Steady incident flow past a circular cylinder. Let's see. Okay, this is a steady incident flow. Velocity u passing by this cylinder, circular cylinder. This is a two-dimensional. Assume infinite length in the direction perpendicular to this board. Okay, if we define this angle as theta, and the radius of this circle is A, we assume steady flow. Okay, we have the flow is irrotational, which means we can use potential theory. It's also incompressible, which means rho is zero. Rho is a constant, and inviscid means no zero viscosity. Okay, we're gonna use potential theory to solve this problem. You probably all know that the potential can be written as okay, U minus okay, it's written in polar coordinate. You can get this from any basic fluid mechanics class, and I assume you have learned this before. It's just the potential due to this steady incident and also a dipole at the center of this circle. So the superposition of these two. One part is due to the steady, and this part is due to the dipole. Okay, if we trying to figure out the velocity on the surface in the tangential direction, which is we define as external UE. This is nothing but d theta. Okay, this one gives at r equals to a. This one gives us 2u sin theta. Okay, this is the velocity at the point at r equals to a. So based on Bernoulli's equation, A and R. A is the radius of this circle. Radius. Okay, don't get confused by here. R is the upper. Okay, if we put the origin at the center of this circular, okay, we can draw any. We can find any vector here. It's R theta, right? This R is like x, y, z. R theta is like x, y, z in rectangular coordinates. This is in polar coordinate. But any point in this plane can be determined by a given R, given theta. Suppose, let's say R is equals to a theta equals to 3 pi over 2, right? 3 pi over 2 is here. And R equals to 2a gives you a point here. Well, this is 2a. Well, I'm not going to do this. This is too confusing. Let's see another. So have you ever heard about a polar coordinate? Yeah, I guess so, right? Steady flow. So now let's see, I'm trying to figure out a point at r equals to 2a. This is approximate 2a. This point can be determined as pi, right? This is the coordinates of this point. So this is r. If you write in general form, it's r. This is like x, y, z in x, in a rectangular coordinate system. Okay, and this form is just due to the transformation between the rectangular and the polar system, and you'll get more complicated forms for spherical coordinates. Okay. Based on Bernoulli's equation, if we assume at the far upstream end the pressure here is P infinity or P now, it doesn't matter, just a symbol, okay? And we try to figure out the force on the surface of this circular. Okay, we have P at this point, pressure, and U, E, we know, right? Squared P infinity, right? This is Bernoulli's equation. So therefore, we can define a pressure coefficient is P minus P now, right, as this. And the result of this thing gives 1 minus 4 and sin theta squared. Okay, you plug UE as this one. Okay, you got this coefficient. What it looks like, so if I draw a figure, okay, this is theta from 0 to pi, that's 180 degrees, and this is 90, this is 45, and 130, 50, 35. Okay, this is CP. So the magnitude, the maximum would be 1, right? Here. The minimum would be, this equals to 1, right? And then it's minus 3. Here. Minus 2. Minus 1. 0. Okay? If I draw a figure, it would be right? This is the pressure coefficient. If we do an integration from, that's the pressure all over the surface, that's what do we have? The total force on this circular is what? You can make a guess. Yeah, it's 0. The total force on this circular cylinder is 0. This is the so-called D'Alembert's paradox. So based on those assumptions, based on our mathematics, we figure out the total force is 0. But in reality, there's always drag force, frictional force, viscous force. You know, this is the same term on this cylinder. It doesn't match the physics, the reality. So this is why we call D'Alembert's paradox. Okay. So what happened? Why we have this paradox? You do know what is a paradox, right? It's conflict. So as I mentioned at the very beginning of the class, we are engineers. We make assumptions. Whenever you have something that against the physics, you go back to look up your assumptions. Which means in one of the assumptions here, we have it's not valid. Which term? Actually, there are lots of terms, but most because we assume non-invasive. In reality, there is always viscosity, and on the close to the surface of this cylinder, we have boundary layers, and we have flow separations. So, if we do a real situation measurement, we're going to end up with something like this for a given Reynolds number. Okay, the first half is relatively okay, but the second half is totally off. So this asymmetry gives us some non-zero force. This is for Reynolds number equals to 8.1 times 10 to the 6th. Okay, this is from experiments. Okay, so the reality is like this. This is, as we mentioned, this is due to the presence of viscosity, which introduce boundary layers close to near the surface of the cylinder. We also have flow separation, which results the non-asymmetry of the pressure distribution around the cylinder. Okay. Now if we do measure the total force, I mean the drag force, the viscous force of this cylinder, and find its F, we can define the so-called drag coefficient. We have seen this symbol many times as, okay, this is the coefficient per unit length. Typically, we have to do model tests to determine this coefficient. Okay. Since here we have flow separation, it's of interest to look at the weak, the flow behind this cylinder. There's one interesting phenomenon is the so-called vortex seeding. Okay. We have a cylinder. Assume the flow, when the flow passes this cylinder, we have separation points, typically. So it's for a laminary boundary layer would be much earlier, but for a turbulent boundary layer it's around 110 degrees, and we have this separation. Okay, one side have the separation, on the other side Oh. Okay. Much better than one in my nose. Okay. So in the starting stage of this vortex shading, a symmetric wake develops. That means the two vertex here and here is like is symmetry. However, starting stage symmetry. However, due to instability, asymmetry develops. Due to instability. So the consequence of this asymmetry is that the vortices are alternatively shaded from each side of the cylinder. So in reality, if we see, okay, this is one line, this is one line, here this is the stringer, we see one vortex is like here, here, and here. So the other side would be the opposite direction. Okay. This is L, and this would be L over 2. And if we assume the distance between here is H. Okay? It's like this. One comment about 70, 80 years ago shows that there's theoretically, so there's a relationship. One comment. Oh, there's a good. Hey. Comment. Ooh. One comment shows theoretically that H over L is pi over 1 over pi cosine minus 1 square root of 2. This is approximately 0.28. So therefore, also the vortex shading period can be estimated as T d U is the incoming velocity, flow velocity. This is Straub number. Straub number. Okay. Here, in his case, is this. Okay. Vortex. Okay. So we know that the vortex shading introduce oscillation forces that will excite the vibration of the structures. So when the vortex shading frequency frequency is close to the natural frequency of the structure. The natural frequency of the structure. Vortex induced resonant oscillations occur. Okay, the keyword, not keyword, important thing is close to. We know from structural dynamics when the frequency of the excitement force equals to the natural frequency of the structure, we have a resonant response or resonant oscillation. Here in this VIV thing, we have a special phenomenon called lock-in. What I was trying to explain this to you, but let's define a few parameters. D is the structural diameter. The natural frequency of the structure is Fn. Okay, we have a current velocity, uc. That's the steady flow velocity. So from this we can define reduced velocity, right? Recall the vortex shedding frequency is Strouhal number times uc over d, right? If we have a change in uc, the shedding frequency is going to change, right? And this changing of uc is corresponding changing to ur, because natural frequency and diameter of the structure for a fixed for a given one won't change. Okay. Now let's look at this figure. We have one axis as ur. That's here is changing from 5, 6, 7, 8 is changing. Okay, this is the response frequency normalized, non-dimensionalized by Fn. That's the natural frequency of the structure. This is 1, this is 2. If we assume the frequency of the structure, oscillating structure, is Fc, this is not necessary to be Fn. It has to be the excitement frequency, right? External force frequency. So, but we know that when this Fc over Fn equals to 1, we have a resonant oscillation. Also, we have another curve. This is Fv over Fn. So we know that the oscillation will, resonant oscillation will occur at this point, this single point. Okay, this is based on our knowledge from the structural dynamics. But if we do observations for the VIV, we found that it's not a point. It's in certain range. it should follow this line. However, we found that in this range, this is C1.5 to, in this range, the vortex shading frequency does not follow this definition, what it should be. Instead, its shading frequency follows the natural frequency of the structure. So in this range, we have a lock-in region for the resonance oscillation. So the point is, it's not a point, it's in a range. This gives us, very much trouble, since we know the resonant oscillation is much more severe than non-resonance oscillations. The amplitude of this oscillation, if we do measurement, we can see is fairly large. If we see this parameter is RAO, okay, this is the oscillation amplitude over the diameter. This is for illustration only, right? In this range. But outside this range, if it's non-resonant oscillation, the amplitude would be very small. But however, in this locked-in region, it's very, very large. The consequence of this VIV is, first, it increases drag force. Okay. Oh, by the way, so far there's no sound physical principles can predict what really happened in this area. Okay, this is a very hot research point right now in the offshore industry, because it has a lot of consequences. First, it increases drag force. It increases the vibration amplitude, right? Certainly, if you have risers, this is a TOP, suppose, and seafloor, you use risers to get natural gas or crude oil from the sea bottom. You want this stay stable here. You don't want the risers doing funny things. Gives very large damage to your structure. And also for FPSO, the loading buoy, you don't want it when you do the crude oil transportation from the ship, from the offshore to the ship. You don't want that connection oscillating too much. Okay. There, on the larger scale, a spar, like a spar is a large platform, right? Have a large platform. You have these mooring lines, right? The spar is a large cylinder. There's current pass below, and this platform, you don't want it doing having large motions. Okay, so there are a few measures or methods we tend to use to reduce VIV. So one of the common methods is we put streaks, it's called helical streaks, around the, I don't have a model, but around the hull of this offshore platform. This can suppress the VIV. So some others, using this phenomena to increase VIV actually. Why do they want to increase the vibration? If you want to harvest the current energy, like to generate power, you want large motions. You put a cylinder in the ocean or in the river. When the current through, you want the motion of this cylinder as much as large as possible. So they actually do some specific designs, by changing the surface roughness and other things to increase the maximum amplitude of the cylinder so that they can harvest more energy from the current. So harvest energy, current energy. Actually, there's one professor at the University of Michigan have done quite a lot of this work, and he actually run a business in this area. It's called We Watch or something. VIV alternative clean energy something. So okay, anyway, this is a very hard topic and certainly unsolved area if you wanna, and it's very important to our ocean engineering. So now let's look at the current force. Current forces on a cylinder. Well, here cylinder means like a risers, morning line, or the structure of this bar, the hull. No, in general, we use, unfortunately, well, and we have no other. Okay, here is the drag coefficient. This is the projected area, and this is current velocity. It's very simple. And the difficulty is how do we determine this CD? That involves a lot of experiments and a lot of experience in this area. Okay. When it comes to compute the current forces on a ship, it's like this. We have a current going this way. We have a ship going to this direction. The angle, the heading angle and the current is better. Okay, so we have to use empirical formulas too. Okay. So in the longitudinal, direction. So we typically use this formula. Reynolds number -2 squared rho SU squared cosine. Okay. This is what? This is like CD, right? And recognize what is this? This is U U in the Morrison equation, right? So all the efforts are putting on how to determine this CD. Okay, in transverse direction, longitude. When I said longitudinal, I mean longitudinal of the shape, and transverse is this direction. So what are we gonna do? So what we are doing is trying to figure out. Okay, it's like a strip theory. If we can measure the coefficient on this small section as a function of x, if let's go, this is x, right? And we can do many measurements, right, to figure out this drag coefficient as a function of the cross-sectional area in this longitudinal direction. We can figure out the force the integration of this. So this gives us a equivalent total CD. It's still CD. Okay? So this CD is a function of many factors. The presence of the what we talked about was a fully submerged cylinder. Now if we're talking about shapes, we have a free surface, right? The presence of sea surface indeed can affect this drag coefficient. Typically it will reduce the magnitude of CD. Okay. So CD free surface can reduce CD. Okay. What other effects have CD? So the flow itself, so it's more steady or more fluctuating, right? Like the laminar flow versus turbulent flow, right? Also, for a smooth cylinder, we can have a critical Reynolds number, and as the structure or the shapes in the operation doing for a long time, the sea growth will cover the surface, right? That will affect so smooth becomes non-smooth. So this will change the CD, right? And for stability considerations, we put a belch and Q on the body. We have, so this has effects on the CD, and also for a long, even the shape itself is long. When at the bow and the stern, the two-dimensional assumption is not really effect. So we have a three-dimensionality effect. Okay, there are a few other things in the computation of the momentum, the moment that I did not present here. That's much more complicated. It involves more math. So I don't think I got enough time. So let's quickly go through the Van force computation. Van force is similar to the way we compute the current force on structures. So there are when forces. Okay. Typically, when we do this, we need rules or principles, like rules from ABS, rules from API, American Petroleum Institute. And I'm sure you know ABS, right? American Bureau of Shipping. Bureau of Safety or Shipping? I think it's Shipping. Okay? Huh? Yeah, I do think. So, this force so a lot of this is the wind speed, and this is the height coefficient, and this is the shape coefficient. This is the projected area in meters. Okay, and you have to look up those things when you use this formula. Everything is in metric unit. So the other is API formula. U is the wind speed, CS is the shape coefficient. And here is U10 actually. And this U is not. This is a U measured at a certain level. So that's the reason you have a height coefficient. And here this is U10. You don't have you only have a shape coefficient. So surely this 2CS is not the same because it's not from the. It could be the same. It's from different rules. Okay.